sit there or should I sit there?
Sure, you can move those buckets if you want. All right, we'll go ahead and get started now. Can the people who are on Zoom, can they hear me and can you see the slides?
Yeah.
Can the Zoom people hear me and can you see the slides?
Yes, we can hear you.
Yes.
Okay, thank you. Okay, so we'll go ahead and get started then. What we're going to do today is just kind of quickly go through chapters 1 and 2 in preparation for the exam on Wednesday. And so as we go through this, if you have any questions, please ask and I'll try and answer them. A couple things I wanted to mention about the exam. So the exam's this Wednesday and it'll have 32 questions. Hold on a second here. Okay, it'll be, as I was saying, it'll be Wednesday, it'll be 32 questions, multiple choice and true, false. Some of them will involve calculations. There'll be a 60-minute time limit, and it'll be set up that you can take the exam during the class period. So on Wednesday, there's no need to come to the classroom. You can take the test from wherever you want. So that's the plan for the exam on Wednesday. Any questions about that? Okay, let me see. I think someone else is clicked in. So. So let me just go ahead and repeat that because some people just dialed in. The exam is Wednesday, 60-minute time limit. It'll be given during the class time. So it'll open at 8:30 and then go through the end of the class. There's no need, if you were scheduled to be here in class on Wednesday, there's no need to be here. You can take the exam from wherever, home or wherever you're at. So just like last time, the test will kind of get graded automatically. So you'll get your scores back pretty quickly. I'm going to set it up so that the next day, the answers will be available if you want to see the answers. All right. Okay, so as we think about what we've done in these first two chapters, one of the first things we talked about was the scientific method. And so here's kind of the process of the scientific method. You have some observations, you collect some information, and what's the first thing that we do based on those observations? We formulate a hypothesis. And then we test that hypothesis through some experiments, and then based on that, we get a theory. So what's the big difference between hypothesis and theory? The big difference is the hypothesis is just based on some initial observations. So we don't know exactly what's going on. We see some things, and we kind of make a best guess at what it means. The key thing there is, with the hypothesis, that's really early, based on just some observations. We haven't done any controlled experiments. And so when we get to the theory, we've gone through that experimental phase. Doesn't mean we're totally finished, but at least we've gotten some data. So that's a key thing to remember there. These are those definitions of the different phases that you go through. And once again, hypothesis is that initial attempt based on some observations that you had. Experiments are what we use to test that hypothesis, and that's a controlled observation. So you design an experiment where you control some variables to see what happens, and then based on that, you get a tentative model to kind of explain what's going on, and that's the theory. If all this stuff works out and you're able to get a mathematical expression and things like that, then you eventually get to law. But the key thing to remember here is really what's the difference between a hypothesis and a theory.
Professor, our screens are frozen.
Your screen is frozen. Okay.
Yes, we're still on the first slide.
Oh, okay. Well, let me stop sharing and then I'll reshare. If that fixes it. What do you see now? Oh, probably nothing, so I'm not sharing. Hold on. Okay, can you guys see the different slide now?
Yes.
Okay. And then did it advance?
Yes.
Okay. So if we talk about how in chemistry we're studying matter, and two of the things that we discussed was the state of the matter and the composition of the matter. So state of the matter would be things like, is it a solid, is it a liquid, is it a gas? So in other words, that physical state of the material. The composition of matter is, well, okay, you have that solid or you have that solution. What is it made up of? The example you often see is water, where you have solid water is ice, liquid water, of course, is liquid, and then water vapor. So you have water, in each case, it's H2O, but depending upon if it's solid, liquid, or gas, it's in a different physical state. And water is an easy example, but a lot of things go with that. So then we talk about classification of matter, and we base it on the composition. So this flow chart kind of walks us through things. And one of the key things is when we look at matter, we say, is it uniform throughout? If the answer is no, it would be a heterogeneous mixture. If it's yes, it'd be a homogeneous mixture. Can anyone think of a heterogeneous mixture that you've worked with recently? Yeah.
In our last lab with the sand, the salt, and calcium level.
Right. And in your last lab that you did, you had that sand, the salt, the carbonate, and you think about that, you put that into solution. That was the first thing you did, right? And what happened? The sodium chloride dissolved, so that went into solution, but the sand and the carbonate, the calcium carbonate, did not. So in that case, that solution that you made up would be a heterogeneous mixture. If everything would have gone into solution, if everything would have dissolved like the sodium chloride did, then it would have been a homogeneous mixture. And then that would have taken us down the yes path after this first question. And then it asks us, does it have a variable composition? Well, if the answer is no, then it's a pure substance. So if you think of, for instance, so I made those samples up for the unknown, right? Just weighed out the 3 amounts of them. But what I did is, for the sodium chloride, for instance, I had a jar of sodium chloride, and I weighed some of that out. That whole jar of sodium chloride was all sodium chloride. So throughout, no matter where I pulled the sample out from that jar, it was the same. So in that case, you would say, did that jar have variable composition? The answer was no. So that tells me it's a pure substance. It's just sodium chloride in there. If you think of that sodium chloride that dissolved in the water, well, it's homogeneous with regards to the first question, because it's uniform throughout. But the stuff that's in there is a homogeneous mixture because it has water molecules and it has sodium chloride molecules. So that's kind of the difference there. If we go on this pure substance path, it asks, does it contain more than one kind of an atom? If it was just sodium or if it was just chloride, then it would be just the element. You would say, no, it doesn't have more. But because, for instance, in that jar I had sodium chloride in it, that's 2 different atoms, and so it's not an element, it then becomes a compound. So this kind of flow path here of thinking about how you classify matter, you should be comfortable kind of making those kind of decisions. We talk about substances being either elements or compounds. And an element is simply when you have it and it can't be decomposed any further. So a compound, it can be decomposed further, and compounds will have more than one atom in them. Atoms are the simplest thing that we'll talk about when we talk about describing building the molecules. An element is only one type of atom. So there's nothing we can do to it to break it down to make it a different atom. A compound, however, has atoms from 2 or more different elements. And as we said before, you can break that down and decompose it into the more simpler forms. One of the things we talked about was there's a lot of elements. Currently, there's 118. But when you look at these 2 examples, one, the Earth's crust, and then the other, the human body, what do we see? We see some amounts by mass of the different elements. And the big thing we see is we see in both the Earth's crust and the human body, oxygen is the biggest player. We also see carbon in the human body, hydrogen, and then some other things. In the Earth, we see silicon, iron, aluminum, and calcium, and a few other things. So even though there's a lot of elements out there, when you look at the composition of things, there tends to be a handful of elements that dominate which is the most popular, the most abundant. So on the human body, why isn't water listed? We got a lot of water in us. Why isn't that listed? I'm sorry, what did you say?
It's not an element.
It's not an element, right? So we're not talking about compounds here. We're talking about elements. So in other words, stuff that's on that periodic table. One of the things that I asked you to do, and you can see it here in red, is memorize the elements and their symbols. And here are just some examples of some of the more common ones: carbon, fluorine, aluminum, bromine. You see the list there. So the expectation is that these more common elements, you know the symbol and you know the name. Some of them are pretty straightforward. You see like carbon, fluorine, hydrogen, iodine, nitrogen, oxygen on down the line. Those all kind of make sense. You get over to the right-hand side with copper, iron, lead, mercury. Those have a little bit different origin of where those names came from. So those aren't as easy to remember. So those you have to put a little more effort into remembering what those symbols are and for which elements. So one of the expectations for this test is that you will know the element names and then the associated symbols. And here's the periodic table that we talk about a lot. We see the stair-step dark line there. Does anyone remember what that means? That's the divider between the metals and the non-metals. Remember, to the left of that stair-step are the metals, to the right are the non-metals. The ones that kind of are along that are the metalloids. And so what we see is there's a lot more metals than non-metals. The other couple things I'll point out is we see the columns are labeled 1A, 2A on down the line. And then the rows have labels too. And remember, we talked about periodicity of some of those and how we can get some information based on what column it's in or what row it's in. And we'll talk about that a little bit more. So I think the first law that we learned was the law of constant composition, or the law of definite proportions. And what that tells us is that compounds have the definitive composition. So what that means is that if you have a particular compound, let's take water again, for instance, H2O. If it's truly water, it's always going to be 2 hydrogens and 1 oxygen. That doesn't change. If that changes, if it's no longer 2 hydrogens and 1 oxygen, it's not water, it's something else. And so this all stems back to this law of constant composition and the law of definite proportions. So it's important that you remember this, because this is really one of the fundamental things that we believe in chemistry, and we know is true, is that compounds don't change. If it's a particular compound, it's always going to be that composition. If we react it or do something like that and change it, then it's no longer that compound. So let's talk a little bit about classification of matter and look at mixtures. So mixtures will have the properties of the different components that make them up. So think of the sodium chloride example again. You know, we know from our lab that if you put sodium chloride in water, it dissolves. Well, sodium chloride, as you know, is salt. And think about it. If you had a glass of water and you took a sip of it, it would taste, you know, water doesn't really taste like much of anything. So it had that kind of water, nothing taste. If you took some sodium chloride and put it in there and stirred it up and dissolved it and then tasted it, you suddenly now, it would still have the wet taste of water, the wet feel of water, but now it would be a salty taste, and you wouldn't want to drink that. So that's an example of where you've mixed the sodium chloride with water, and now it has properties of the water, and it has properties of the sodium chloride. When you have mixtures that the composition varies throughout the sample, it's heterogeneous. And this goes back to that early on when we're going through that flow chart of composition of matter. And we had some of those flow chart questions. Heterogeneous just means that it's not the same. So if I sample one spot versus another spot and I analyze that, I may get something different because it's not consistent throughout. Whether if it's homogeneous, doesn't matter where I sample in that container, I should get the same answer if I analyze the material that's in there. Homogeneous mixtures are also called a solution. Now, for me personally, when I think of solution, I always think of liquid. But technically, by definition, the solution can, although it's usually a liquid, it can also be a solid or a gas if it's homogeneous throughout. So it seems a little odd to say that something solid could be a solution, but by just definition, that's what they're calling everything that's a homogeneous mixture is a solution. So when we think of the properties of compounds, we think of two things. We think of physical properties and we think of chemical properties. So physical properties are the descriptors of how something looks, feels, things like that. And then chemical properties involve some change to it. So physical properties, you can do something to it and observe the physical property, but when we talk about physical properties, we're not talking about doing any change to the substance. And so, you know, chemical change to the substance. So some examples are color, odor, density, melting point, boiling point. If we look at melting point and boiling point for a moment, boiling point, you figure you heat it up and it becomes a vapor. And that temperature at which it becomes that vapor, that's the boiling point. If you think about it, if it's truly a physical change and you're just volatilizing it, the composition stays the same. So if we were to trap that gas and then analyze it, it would be the same compound as what we started with in the liquid form. Same with melting point. If you have a solid piece of solid and you melt it, and just melt it, not decompose it, if you analyze it before and after melting, it'll be the same stuff. So that's the key with the physical properties. You can observe them without changing it into another substance. When we talk about chemical properties, they can only be observed when it's changed to another substance. So when you think of chemical properties, the way I always try and remember it is I think of chemical reactions. And you think of chemical reactions and you're taking two or more things and having them interact on a chemical basis, and you're producing something new. So this idea of chemical change is really what we're talking about when we're looking at chemical properties. One that you see, and this was labeled on the alcohol that we had in the lab, was flammability, that it was flammable. That means it burns easily. And so you have some oxygen and you have an ignition source and you can burn, and then in that case it would convert the alcohol to something else. It wouldn't stay alcohol. So it volatilizes, but it's actually a combustion reaction. So if you then trap that vapor, it wouldn't be the alcohol anymore. So if plants make sugar from carbon dioxide and water, is that a physical or chemical change?
Chemical.
Chemical, because we're having a reaction. We're taking carbon dioxide and water, changing those molecules and making it into sugar. How about if water vapor forms frost? Physical, right, because we haven't changed the water, we've just changed the physical state of it. And then finally, a goldsmith melts it, a nugget of gold, and pulls it into a wire. Physical, right, because we haven't changed gold, it's still gold, it's just a different form now. Just instead of being a chunk, a nugget, now it's a wire. When we talk about properties of a substance, there's two types that we discussed. One is intensive and the other is extensive. Remember, intensive begins with I. That's the one that's independent of how much stuff we have, of how much of that substance we have. So whether we have 1 gram or 1 kilogram, the property doesn't change. And some examples of that are density. Does anyone remember what density is? What's the definition of density? Yeah.
Mass over volume.
Mass over volume, right. So that mass over volume, that ratio never changes for that substance, whether you have a little sample or a big sample. Boiling point, color, melting point, all these are other examples of the intensive properties. The nice thing about intensive properties is they can be used to help identify what something is, because it's not dependent upon how much stuff is in there. If you go on and take organic chemistry, one of the things they do in the lab there is they'll do a synthesis of material. And one way to see how pure your material is to take the melting point. If the melting point is pretty close to the literature or theoretical value, then you know you probably made a pretty good synthesis. If it's not, then that tells you there's something else there mixed in with what you tried to make. And so then that would tell you you didn't have a good synthesis. So these intensive properties, because they're not dependent upon how much material you have, are really useful to kind of get information about identifying a compound or a substance when you don't know what it is. Extensive properties, on the other hand, are dependent upon how much you have. So things like mass, volume, energy, all of those are dependent upon how much you have. You know, think about the energy thing. If you eat more food, it gives you more energy. You don't need it all, you don't have very much energy. So that's a case there of where that's an extensive property, the energy is. It's dependent upon the amount of mass, the amount of stuff that you have involved. So once again, just to talk about this difference in physical and chemical, physical changes don't change the composition of the substance. Chemical changes result in new substances. So when we talk about those chemical changes, if nothing is changing to that compound, then it can't be a chemical change. If something does change, if it converts to some other substance. And so at this stage, you may not understand or may not know how that conversion happens. But if someone tells you, oh, we took this type of molecule and created another type of molecule, by definition, it's got to be a chemical change because we violated that first law of constant composition. Remember, we talked about that early on, that a molecule doesn't change its composition. It's always the same. If it does change, then it's had to have gone some type of chemical reaction, chemical change. So I want to talk about this one just for a moment. So this is the one where the penny was put in the nitric acid, and the nitric acid reacts with the penny to form copper nitrate and nitrogen dioxide. So one interesting thing about this is that we got a color change in this as well. And a lot of times when you do reactions, you can get a color change, or you can get a heating feel, so giving off heat, or it can feel cool, or you can get a precipitant or something like that. So there's some physical changes. So that was what we would have done in the second part of the lab if we would have done that, was looked at some of these. Because sometimes those kind of changes that just are what I would call observational changes give you a feel for it that something might be going on from a chemical basis. You can't know for sure, but a lot of times it is a tip-off. And this was an example of one. So when we have mixtures, we often like to separate them. Once again, you guys did that in the lab the other day where you separated out the three components to try and figure out how much of each was in there. And the one you used a couple of times was filtration. And this probably hopefully looks familiar to everyone. So in filtration, you're separating solids from liquids, basically. So in your case, you use that filter paper to pour the solution into there. The solids got trapped on the filter paper. The solution went through. And then you could go, you could take that initial liquid solid separation material and you could do some things with it, right? If you think about that sodium chloride experiment, what you did was the next thing. You did a crude distillation. Now, you didn't have a condenser and a setup like this, but that's essentially what you did, was a distillation, kind of without collecting the distillate. Because what you did is you used the difference in boiling points of the sodium chloride and the water so that you could heat it up, and the water evaporated off, right? It boiled off, and the sodium chloride was left behind. And so that allowed you to then separate the water from the sodium chloride and determine how much sodium chloride was in your sample. Now, as you learn, there's some experimental things you have to deal with, the splattering, controlling your heat source, things like that. But fundamentally, what you were doing was using a difference in boiling points. So sodium chloride doesn't boil. and water does. And so you're able to use that difference in boiling points to drive off the liquid and be left with the solid. Okay, and then now, what was the key takeaway on chromatography? Does anyone remember what the key takeaway on this slide was?
It's your specialty.
It's my specialty, it's my favorite, okay? And as I've said multiple times, you have to remember that, that's very important. Okay, let's talk about energy a little bit. We had some definitions on energy and related to energy. We said energy is the capacity to do work or transfer heat. Then we said work is the energy transferred when a force exerted on an object causes the displacement of that object. And then we said heat is the energy used to cause the temperature of an object to increase. And then finally, force is any push or pull on an object. So the example we had here was the woman about to kick the soccer ball. And so their energy is about to be transferred from her leg to the ball, and then the ball will get displaced, to go flying in the air. Then the example for heat was just boiling water. So you're putting energy into that water to raise the temperature and then get it to boil. So some definitions around energy that are pretty useful for us. When we talk about energy, there's two basic forms of it: potential energy and kinetic energy. The difference there is kinetic energy is the energy of motion. Potential energy is, just as you say people have potential, it's something that is there and can happen but hasn't started yet, okay? And potential energy depends on where something is relative to its surroundings. And here's a nice example here of where this woman's on a bike at the top of a hill, not doing anything, but seeing the steep slope. So we look at that and we see that there's zero kinetic energy. Because remember, kinetic energy is the energy of movement. So she's not moving, she's just sitting there waiting. But you see her position. She's up on top of the hill. We know if she goes downhill, she's going to go pretty quickly, right? Because we know there's potential energy there. If she was sitting at the bottom of the hill and waiting, there'd be no potential energy because there's of her relative position to things. Now in the next picture, she's going down the hill. So her kinetic energy is increasing. So she's going faster, faster, faster as she goes down and builds up that speed. But her potential energy is going down. Because as she goes down that hill, her position relative to where she started, and she had all that potential energy, is decreasing. So the key things to remember here are kinetic energy is the energy of motion, of doing stuff. Potential energy is how well are you set up to do something. In the first picture, she's set up to really go fast because she's at the top of the hill. The second one, she's going down the hill, so her potential energy has gone down, but her kinetic energy has gone up. We learned a formula about kinetic energy. Kinetic energy equals 1/2 times the mass times the velocity squared. That allows us to calculate kinetic energy if we know velocity and mass. Okay, I just want to say, I think a little later we have an example of a kinetic energy calculation, but before we get to that, I just want to remind everyone that velocity is squared. So if you know the velocity and you want to use this formula, you got to square that term. The other thing is the mass. The mass and the velocity both need to be in the right units to fit in with joule. Does anyone remember what the units for the mass and the velocity needed to be to make this formula work? Okay, 1 joule, the units for that is kilograms meters squared over seconds squared. So if it's meters squared, seconds squared, what would be the units of velocity that you would need? It would be meters per second because we're squaring that term when we put it in there, okay? Like I said, I think in a few slides we have another example of that. So it'll be a little clearer when you can see it. Okay, so numbers are important in chemistry because usually when you're doing experiments in that, you're doing it to generate some quantitative data and you want numbers to explain what your data is telling you. And some key things there are you need units of measurement, you need the quantities, you need uncertainty in measurement, and two things that are near and dear to our hearts, significant figures and dimensional analysis. Significant figures tells us that if we have one number that has, say, 3 significant figures, and we have another number that has 4 significant figures, we multiply those. We don't write all those numbers that our calculator or our spreadsheet gives us. Because a lot of those numbers really don't have anything to do with the measurement we did. Think again, once again, back to when you were in the lab and you used the balance. When you use the top loading balance, you get 3 digits past the decimal, no more. So you know that the most significant, you're not going to get more significant figures than what the instrumentation that you're using to collect the data can give you. You might have numbers, but they become meaningless when you start doing the math because it all goes back to the experimental part. That's the nice thing about doing the labs is hopefully you'll start to get a feel for how kind of the practicality of why some of these things are in place. Okay, we talked about some of the units of measurement. These are the SI units. Where we have length, mass on down the line, meters, kilograms, Kelvin for temperature, things like that, or what's standard. Here we had an example of the soda can where it says 12 fluid ounces and underneath in parentheses 355 mils. So everything that we'll do in the lab will be metric. Okay, so no pounds, no miles, things like that. It'll be grams, meters, degrees C or K, moles we'll get into a little bit more later in the semester. And one that we want to remember is volume is cubic centimeter. Cubic centimeter is the same as a mil. Prefixes. Once again, we have read, memorize the prefix, abbreviation, and meaning. So that's an important thing. So we see some of these, we see kilo is 10 to the third, the small k, deci, 10 to the minus 1, the d, centa, 10 to the minus 2, milli, 10 to the minus 3, on down the line. Down at the bottom here, we see that definition of joule that we talked about, where 1 joule equals 1 kilogram, meters squared, seconds squared. So that's important because that needs to be known to fit into our kinetic energy equation. This is just kind of a repeat of that previous table, just breaking out some of the more common ones of what the multipliers are for giga, mega, kilo on down the line. So these conversion things and understanding the difference between a kilometer and a meter and a centimeter and things like that, that's where the dimensional analysis comes into play. So you should be comfortable taking those relationships and say if you go from kilometers to millimeters, being able to do that conversion over using those type of information that's in that table. When we talk about mass, that technically mass and weight are not the same. Weight is based on gravity, mass is not. And so when you talk about how much something weighs, you should be saying mass. Volume is a derived unit. The one that I think people got a little confused on the quiz was milliliter. Milliliter is the same as a cubic centimeter. And so when you talk about density, sometimes it's written grams per mil, sometimes it's written grams per centimeter cubed, sometimes it's written grams per cc. Those are all the same thing. And it comes back to this definition here of a milliliter is a cube, 1 centimeter on each side. So that's where the centimeter cube thing comes from. We talked about the different temperature scales. We had Kelvin is 273 plus degrees Celsius. And then there's Celsius is the common metric way of measuring temperature. Fahrenheit is what we get on the weather report when we watch the news. The keys here, and this makes it much easier to me at least to remember, is with the Celsius scale, freezing point of water is 0 degrees C, boiling point is 100 degrees. And then once again, Kelvin is degrees C plus 273. Okay, let's talk about energy again. We talked about it a little bit before, and we said that kinetic energy is 1/2 mass times velocity squared. And we said that a joule, which is usually the energy unit that we use, that's the most common one, is kilogram meter squared per second squared. And when we talk about the nutritional calorie, that's the capital C1, but really it's a kilocalorie. If it's not a calorie, it's a kilocalorie, what does that mean? What would you multiply? If I told you it was 1 calorie with small c, and I asked you to tell me how many, convert that to kilocalories, what would you do? What would you multiply it by?
1,000.
Sort of. You would multiply it by 10 to the minus third to go from calorie to kilocalorie. Because 1,000 calories equals 1 kilocalorie. Does that make sense?
Oh, yeah.
Yeah. But you have the right idea. It's 10 to the third is the difference. But and one way you can remember that so you don't get it flipped is if you had 1 calorie and then wanted to know how many kilocalories, you know it takes a lot of calories to equal a kilocalorie. So then that 1 calorie's got to be less than 1 when you convert it to kilocalories. Maybe I just confused you more, I don't know. So this was our kinetic energy calculation that we went through with the baseball. Kind of appropriate for this time of year with baseball season going on. You had a weight of a ball in ounces. You had a speed of a pitch, 95 miles per hour. And we wanted to find out what the kinetic energy was. And so a couple things. We know the formula for kinetic energy. That's the 1/2 mass times velocity squared. We know the units for joules. So that tells us that the mass has got to be in kilograms and the velocity has got to be in meters per second. So then we look back to the information we were given, and what do we notice? We notice none of those things are in the right units. So we need to go and we need to change ounces into kilograms. And we do that by changing first ounces into pounds, and then pounds into kilograms, and that's that second bullet point there, walking you through that calculation. And then the next thing we need to do is we need to change miles into kilometers. And so we change miles into kilometers and then kilometers into meters to get us into our final meters units. And then we want to change an hour into a second. And that's what's done in the denominator of that. So if we do all that correctly, then plug in our numbers into our equation and do the math, everything should work out. But most importantly, our units will work out. So this is an example of where you had to do several different steps using dimensional analysis to be able to convert the different terms into the right units. So this is an example of why understanding what the prefixes mean, kilo, for instance, and things like that, and some of these conversions, and then using them in a dimensional analysis approach is important. Okay, our old friend density. We were told earlier that it can be grams per mil or grams per centimeter cubed are the most common units, and it's mass per volume. So you did that in the first lab also, is where you worked with that in terms of calculating a density. Here's a simple example of where we wanted to calculate the density of this material. So we took the number of grams and divided it by the number of mils. This was an easy one because all the units were correct. You know, if we would have been in kilograms or liters or something like that, we would have had to have done dimensional analysis to convert it into the correct units. Okay, uncertainty in measurements. So every measurement has some uncertainty in it, has some inaccuracy. And it's always that last significant figure that we're using is the one that has some uncertainty in it. Any numbers past that, we really have no confidence in at all because they don't link back to our measurement tool. And so here's a good example here of we're measuring the size of the quarter, and we have two different rulers, one with more graduations. In other words, it gives us millimeters in between the centimeters, the other one does not. And we see the difference there because of that extra marking in there, we get another significant figure. And as we talked about, we look at the bottom one and we're pretty sure it's at least 2. We know that. But after that, that 0.3 is a guess. Now we can make a reasonable guess, but it's not going to be as accurate as the one on top, because that 3, we've got the markings to tell us where the 0.3 is in that measurement. And then it's just that next 3 that we're kind of estimating based on trying to read it. Accuracy versus precision. Precision is how close, if we do repeated measurements, those measurements are to each other. Accuracy tells us how close are we to the true value. So accuracy tells you if you're right or not. Precision, you can be wrong, but it tells you, boy, I do it exactly the same way wrong every time. So what you really want is you want an assay that's both accurate and precise, because you'd like it to be accurate so you get the right answer, and you'd like it to get the right answer every time. And so that's the precision part. So important to understand the difference of those. I think I said this before, but people use them interchangeably all the time. They are not the same thing. You'll hear people say, we really need to be precise on this. And it's like, you know, you probably mean you want to be accurate. Scientific notation. So I'll just say one comment, and that's the stuff in red again. Please go back and, you know, if you didn't do well on the lab on the scientific notation part using your calculator, please go back and try some of those again. You know, if it's an issue of using your calculator and understanding the parentheses and the exponent key and all that, make sure you're comfortable with that. If you need to go back to your manual or whatever, because all these calculators are different, it's really imperative that you know that. The other thing to remember is when you're doing calculations in the chemistry class, significant figures, you've got to be cognizant of that and be aware of that. For me personally, if you're off by one significant figure or something, I'll get too excited. But when I see a number that has 12 digits to it, and you multiply two numbers that had 3 digits, I'm going to take off on that every time. And I think most chemistry instructors do. Because we're trying with the significant figures to reinforce what you're hopefully learning in the lab, that measurements come from some type of tool that you've used, and those tools have limitation. So once again, I'll say it again, please make sure, especially if you didn't do well on that last part of the first lab, please go back and make sure you can get the right answer. I know for my labs, I put the correct answer in, I believe, and make sure that you're comfortable using your calculator. Okay, so just talking a little bit about scientific notation for the top one, 0.00232. To convert that over, we'd slide the decimal point over to the right 4 places, and then that would give us 2.32 times 10 to the minus 4. The one below, we'd slide the decimal place over to the left 3 places, and so then that becomes 4.531 times 10 to the third. So it's that sliding of the decimal to the left or right that tells us whether it's a negative exponent on the 10 or a positive exponent on the 10. And then we rewrite the number that way. It's real useful for writing numbers that are real big and don't have a lot of significant figures, or ones that are really small, like that 0.000232, without writing all the zeros out, but having it a little easier to see what the number is. Okay, just some of the rules. All non-zero digits are significant. Zeros between non-zero digits are significant. Digits at the beginning of a number are never significant. And zeros at the end of a number are significant if it contains a decimal point. And here we see 3 examples of 3, 4, and 5 significant figures. And the key there is they use scientific notation to show us that in the second and third examples that those trailing zeros are significant. So that's a good example of why you would use scientific notation there. So how many significant figures on the first one? 3. How about the second one?
1.
3, because we have that decimal there and then the zeros. How about the third one? There, that one's 1. The fourth one, 5, because that 0 is in between some digits, non-zero digits. And then the last one, 4, because once again, we have that decimal there, so those zeros at the end are significant because of the decimal. Okay, when we're talking about calculations, the big thing to remember, so on the first one, we're doing a multiplication, and this holds for multiplication or division. How many significant figures are we going to have there? We're going to have 3, because multiplication and division, the number of significant figures is driven by the number that has the least number. So the 24.6 has 3, so we're only going to have 3. Okay, and this next one, 4.6389 minus 2.1, we wind up with 2 significant figures. And the key thing is how many are past the decimal point? And why is it only 1? Why aren't we using the 3, 8, and 9 and all the other stuff? It's because in subtracting and adding, the significant figures are to the right of the decimal are driven by the least number of digits in the numbers we're working with. So in this case, The 2.1 just has one digit to the right of the decimal, so that's why we can only have one there. With that same logic, how many are we going to have on the last one? How many digits past the decimal are we going to have in this answer? We're going to have 1 or 2. We're going to have 1 for that same logic. Okay, our old friend dimensional analysis, this is just where we're using those conversion factors to figure stuff out, okay? We've had some examples of that. Okay, let me pull up chapter 2 and let's go through some stuff on that. Okay, can you see my slides on the Zoom? No? Okay.
No, I don't see any slides.
Okay. Still no?
They're up.
They're up, okay, great. Okay, so law of constant composition, we talked about that a little bit before. This goes back to the stuff that Dalton used to get his theory. The other was conservation of mass. And that tells us that the total mass of a substance at the beginning of a reaction is the same at the end. So we do a reaction, so we've changed what the material looks like, but if we were to add up all the atoms and all that stuff, we wouldn't have created or destroyed any of those. We just more or less rearranged them. And then law of multiple proportions. If two elements form more than one compound, the masses of them that combine together are always in small whole numbers. So using water as the example, it's H2O, it's not H1O½ or something like that. So these were just some key things that Dalton based his theory on, and one of his key discoveries was that based on what he put together in his theory is that elements are composed of a small thing called what he called an atom. So that was pretty groundbreaking, talking about atoms. He talked about how an atom of, say, carbon is the same no matter what. All carbon atoms are the same. That was another big deal thing that he figured out. And atoms aren't changed into different atoms. So atom is kind of that base thing. You can change compounds into other compounds, but the atoms stay the same. So another important thing that he is credited with. And that atoms of more than one element combine to form molecules. So these four things that Dalton came up with in his atomic theory were pretty critical at the time. One of the flaws in his theory, though, is that he thought the smallest particle was the atom. And remember, we talked about a host of things that were discovered that exposed us to the world of subatomic particles. So electrons and associated with cathode rays, radioactivity, the nucleus with protons and neutrons. And so all of this stuff was learned later. Cathode ray, this was an experiment we talked about a little bit. The key thing there is that through cathode ray, they discovered these negatively charged particles. What do we call the negatively charged particles? Does anyone remember that? Electrons. So here's just a little more detail about that, but the key thing here is that cathode rays were shown to be negatively charged particles, which became known as electrons. We talked about radioactivity a little bit. Here's Marie Curie, one of the people involved in that early work. And the key thing about the radioactivity is when that's another example of where they discovered subatomic particles that had energy. And the three that we are concerned about and that were discovered were alpha, beta, and gamma. And the key things there are their ionizing power and their penetrating power. So alpha has the highest ionizing, lowest penetrating, beta is kind of in the middle on those, and then gamma has the lowest ionizing and the highest penetrating. So depending upon what you're trying to do, you would take advantage of those properties of these three types of radiation. If you're trying to ionize something, then alpha would be your choice because it has really good ionizing power. But if you need to penetrate something, gamma would be the one you would use because the ionizing power is relatively low, but the penetrating is high. So Rutherford is credited with discovering the nucleus, where he used some of those alpha particles, observed some scatter, and then came up with a theory that the atom has a dense positive center with electrons on the outside. So the key here is he told us that there's a nucleus there which contains protons and neutrons. So that's why it's positively charged, because the protons have a positive charge, neutrons are neutral. And then this bigger volume floating around is where the electrons can be. And so this idea of having a very small, dense nucleus with the electrons floating around the outside kind of became the basis of what we call the nuclear atom. Because atoms are usually neutral. So in other words, not positively charged, not negatively charged. We have to have, and we know neutrons have no charge. We know that we have to have the same number of protons as electrons to have that charge balance out. The other thing that I will just mention is that when we talk about atoms, we usually talk about angstroms. And the angstrom is 10 to the minus 10th meters. And so a lot of times when you see people talk about bond lengths or things like that, they'll talk about it in terms of angstroms. So that's a real common bond type unit. So a couple things to remember about these subatomic particles, the proton, neutron, and electron, is that the masses of protons and neutrons are pretty similar. And the other thing is, those two are pretty similar, but they're a lot bigger than the electron. So when we think of a weight, when we think of that atomic weight of an element, that comes from protons and neutrons. The electron really, what it contributes is pretty small. So each element has an atomic number. The atomic number is the number of protons in the nucleus. And since there's no overall charge, it also tells us how many electrons are there if it's a neutral charge. But the key thing is atomic number is the number of protons in the nucleus. So the way this is often written is we have the mass number here, we see it's 12. So if it's the mass, it's protons plus neutrons. We see the symbol C, in this case that's carbon. And then the atomic number, it's 6. That tells us how many protons are there. And since it's neutral, it also tells us how many electrons. So based on this information, we can learn a little bit about the number of protons, neutrons, and electrons. You hear about isotopes. Isotopes means you have a different weight for the element. In this case, examples of carbon, 11, 12, 13, and 14. By definition, the number of protons can't change because that's what tells us it's carbon. If it was a different number, if it wasn't 6 for the number of protons, then it would be some other element. So the only other way that we can have that mass change is by varying the number of neutrons. Because we know the electrons have to balance the protons to keep it electrically neutral. And besides, electrons don't really weigh much. So the way to get that change in mass is by having more or less neutrons. And then over on the right-hand side there, it shows some of those examples of the different number of neutrons. So that's what we're talking about when we're talking about isotopes. Let's talk about the periodic table for a little bit. It's the way the elements are arranged, and they're arranged in order of their atomic number. And what did we say atomic number was? What does that tell us? It tells us how many protons it has. So, and actually hydrogen, which is number 1, usually you don't say hydrogen, you say a proton, because you think about it, that's got 1. So in periodic table, you'll see this type of nomenclature where there will be a number, then the symbol, then another number on the bottom, and the bottom one usually has some decimal place, digits past the decimal place. The top is the atomic number, then the K in this case for, what's K? Anyone remember what K is? Potassium, good. We have the atomic symbol, and then finally the atomic weight. So if the atomic number is 19, the atomic weight is 39, we won't worry about the decimals for right now. How many protons does that have? How many? 19. I'm going to go with 20 because I think 39 minus 19 is 20, right? So we know that 19 is the number of protons. We know only protons and neutrons give us the mass. And so if we subtract the atomic number from the atomic weight, we get the number of protons. Okay, the rows are called periods and the columns are called groups. And in the columns in particular, you have similar traits for those. So for instance, on the 1As, those all have +1 charge. 2As +2 charge. So there's stuff like that that you can get just by knowing what column it is. The rows across, you'll get some increases or decreases of things as you go through those. And that's called the periodicity. These groups do have some common names. 1A is alkali metals. That's pretty used quite a bit. Alkaline earth. And 2A, 7A halogens, 8A noble gases. Like I said, the 6A one, I've never used that in my life, but the others I have. So those are some common names that are routinely used. We said before that everything on the left of that stair step on the periodic table is a metal, and things to the right are nonmetals. Metals and nonmetals have some properties. So these are some physical properties here that they talk about. But probably the biggest thing is metals like to donate electrons. So if they donate electrons, then their ions tend to be positively charged. The nonmetals like to receive electrons. So since they're picking up an electron, their ions are negatively charged. And so when you talk about forming compounds, the metal-nonmetal combination really works well because you've got one group that likes to give up electrons and another group that likes to pick up electrons. So it matches up well. When we talk about naming compounds, we'll have subscripts on it, and there are some examples over there that tell us how many of the atoms are there. Some atoms are diatomic molecules, and these are some examples of that. So one thing I want to remind everyone, empirical formula, lowest whole number ratio of atoms of each element. Molecular formulas gives the exact number, so it gives you a little more information. Okay, a couple things I want to just remind everyone about. Common cations, common anions, polyatomic ions. This starts the list of things that you just need to kind of go through and memorize some of this stuff, okay? I mean, we could go through it, but in all honesty, it's just, this is the chemical nomenclature. This is the stuff where you're going to have to go through and memorize these. So please take a look at these. Get comfortable. Here's another table that is good to know in terms of these prefixes and the meaning. So di, tri, tetra, penta, hexa, on down the line. The nomenclature for binary compounds, there's some rules there in terms of I and no double vowels, things like that. The organic compounds, we talk about alkanes and alcohols. And so that back end of that chapter really is going and taking a look at those rules, getting comfortable so that if you get some of those compounds, you'll be able to make them. Okay? So that's it for today. I hope this helped a little bit. Once again, the exam will be Wednesday during the class time. The exam will be accessible at 8:30, and we'll go through the time for the class. You'll have an hour to do it, and let me know if you have any questions. All right, and once again, you don't need to be here for the exam. You can take it wherever you like. All right, thank you.